Section 2.4 is titled Infinite Limits, and these are just a different type of answer that we can get to some limit problems. We see them in particular for rational functions and some trigonometric functions. So to introduce this section, I want to start off with a graph. And this is the graph for f of x equals 1 over x minus 1. One over x minus 1 has a vertical asymptote at x equals 1. And we'll talk more about that in a few minutes. And then it's got two separate pieces that make up this graph. It has got a right-hand piece that's above the x-axis, and it's got a left-hand piece that is below the x-axis. So it looks something like that. So infinite limits are when we get an answer of positive or negative infinity when we are answering a limit question. Now, technically, those limits do not exist. Technically, when we are asking a limit question, we are wanting a finite answer. We are wanting to know an exact y value that it looks like the graph is approaching. So if the graph is approaching in positive or negative infinity, technically, especially if you read the textbook, you'll see this, technically these limits do not exist, but we still write out these positive or negative infinity answers, and I'll write all this down in just a second. But if you look at this graph, this is 1 on the x-axis. The limit as x approaches 1 from the right on the graph of f of x, just looking at this graphically. So if we approach 1 from the right, this graph is going nearly vertical up. So this graph is going up to positive infinity. So that's what we mean by infinite limits. We are getting an answer of infinity. And if we were to do the limit as x approaches 1 from the left of f of x, so try to get really close to 1 following the graph from the left, it's going nearly vertical down to negative infinity. So we are getting an infinite answer for our y value. So these are infinite limits. Anytime this happens, it means we have a vertical asymptote. And the positive and negative on our infinities doesn't really matter. That's not what means the vertical asymptote. Just the fact that we get infinity in some way, shape, or form is what indicates a vertical asymptote. So we can tell graphically that we have positive or negative infinity as the limit. And we can also see that because of the vertical asymptote, we're going to get positive or negative infinity as the limits on either side of our vertical asymptote. Now, because these one-sided limits are pointing in opposite directions, if we were to just ask the limit as x approaches 1 and not specifically say left or right, if we follow the rules from before, because these two answers are different, one of them says positive infinity, one of them says negative infinity, those are two different answers, we would say that this does not exist. Because from the left and from the right, it's doing two different things. If they were going in the same direction, then we could say either positive infinity or negative infinity. So let's look at one more example graphically where they are going in the same direction. Let's look at the function g of x equals 3 over x plus 2 squared. G of x equals 3 over x plus 2 squared. So this is just kind of a rough estimate of what this graph is going to look like. It's going to have a vertical asymptote at x equals -2. And that vertical asymptote splits it into two pieces. But both of these pieces are above the x-axis on either side. So if we were to ask about the limit as x approaches -2 from the left, and then the limit as x approaches -2 from the right, and then just the standard limit as x approaches -2, not specifically left or right. So first from the left, we want to approach our -2. It's going up to positive infinity. And then from the right, going up to positive infinity. And because both sides are doing the exact same thing, we can say that the actual limit as x approaches -2 is positive infinity. Because they match. So this is a good example of why a limit is not always equal to the exact y value on the graph, because technically infinity is not going to be a y value on the graph. And when we have a vertical asymptote, there's not a y value on the graph. That means the graph is just approaching and getting really, really, really close and going up forever. And that's exactly the same thing as what the infinities mean. It just means the graph is going up forever. And that's exactly what the essence of a limit is. A limit is what is the behavior of the graph? What does it look like the graph is doing as we get close to -2? What is the y? What are the behaviors of the y coordinates? Well, they are going to positive infinity. So we're not always identifying a specific y coordinate. Sometimes we are, but not always. So you can't always just look at the graph and look for a specific y coordinate labeled on the graph. A lot of times we're looking at behavior and we have to follow the graph into a point. And these infinite limits are a perfect example of that. So this is how we can do these problems graphically. We can follow the graph in from the left and from the right. We can always do left and right hand limits. If they don't match, that means our standard limit doesn't exist, just like before. If they do match, then we can do our standard limit, just like before. And in the infinite limits, it means we're getting positive and negative infinity as our answers. If the graph is going up forever on the side of our vertical asymptote, it's positive infinity. If it's going down next to our vertical asymptote, it's negative infinity. So graphically is definitely a really easy way to see this, but we also can do this numerically and analytically. So let me label this. And let me also tell you that technically, to be 100% mathematically accurate, technically, these limits do not exist. All of them. But if we are being asked to do these limits, then we are being asked to describe the behavior of the graph. So we're going to say positive infinity, negative infinity. The only time we're actually going to say does not exist is when those two sides don't match up and we're doing this one that doesn't say specifically from the left or from the right. So numerically, the way that we're going to identify these infinite limits is we'll see those y values shoot off to positive or negative infinity in our table. So if we want the limit as x approaches, let's say 0, for x plus 1 over 3x, now we didn't say left or right, which means we have to do both. If it doesn't specifically say left or right, you have to do both. And we're going to do this numerically, so we're going to do it with a table. So remember how we do a table. We're going to put our target value in the middle, and we're going to approach it with negative powers of 10. We're trying to figure out that value. So the farthest away we're going to go is we are going to add a tenth on the right, and then 100th, and then 1,000th. And then we're going to subtract on the left the same values. So negative a tenth, negative 100th, negative 1,000th. And we just need to plug these into the function. I'm going to erase this because it looks like it's part of our function. So we just need to plug a negative tenth into x plus 1 over 3x, plug in negative 1,000th into x plus 1 over 3x, and so on and so on and so on. And then trace these values into the middle and see what it looks like is happening as they come together at 0. So like we said a couple videos back, the fastest way to do this is in your calculator, plug x plus 1 over 3x into your y equals, and put your calculator's independent variable in ask mode, and then you can just type all 6 of these x values into your table, and their y values will pop up really quickly. Your calculator doesn't have a whole lot of space to display those y values. So if you need a more accurate y value from the table, you can always use your arrow keys to move around and highlight your y value, and then the full y value will actually display at the bottom, even though sometimes the value that shows up in the table is only has a couple of decimal points. So let's go ahead and get these values plugged in. And when I plug in a negative tenth, I get negative 3. When I plug in a negative hundredth, I get negative 33. And when I plug in negative 1,000th, I get negative 333. So those values are approaching 0 from the left. So it looks like they are going to negative infinity. As we come in from the right, when I plug in a positive tenth, I get 3.67. When I plug in a positive hundredth, I get 33.67. When I plug in a positive thousandth, I get 333.67. So these values are approaching positive infinity. So the limit as x approaches 0 from the left is negative infinity. The limit as x approaches 0 from the right is positive infinity. What we were asked to do is just the limit as x approaches 0. Well, the left and the right are not matching up, which means this limit does not exist. So this graph, it's got a vertical asymptote. Anytime you have limits approaching positive and negative infinity, you have a vertical asymptote. So we've got a vertical asymptote at 0. And on the left, it's going down. Oops. On the left, it's going down. On the right, it's going up. So it looks something like that. I'm sure that's not exactly how it looks, but it's something similar. So the table works exactly the same way as before. And if they are not coming together in the middle to equal the same thing and approaching the same thing in the middle, we would say it does not exist. Now, analytically is the fun way to do this, because we can tell, once we try direct substitution, we can tell right away if we're going to have a vertical asymptote. So we said in section 3, every single limit problem that you are presented with, if you have the option, you should always try direct substitution first. Unless you are specifically told otherwise, always try direct substitution first. And that's where you just take your target x value and plug it into the function. So these problems that have infinite limits, you're going to see a pattern in the result that we get when we do the direct substitution. If you try direct substitution for the limit as x approaches 2 of 5x over x minus 2, if we just try to do direct substitution, you don't analyze this function ahead of time or do any extra work. You just jump straight into it and do direct substitution. So we're going to plug in 2's for the x's. This is going to be 5 times 2 over 2 minus 2, which is 10 over 0. In section 3, we saw something called indeterminate form. An indeterminate form was 0 over 0. That meant that our numerator and denominator had something in common that we could fix. So indeterminate form, 0 over 0, is fixable. This one that we just tried is 10 over 0. If you tried to ask your calculator what 10 divided by 0 is, you'd get an error. You can't do it. It's not 0 over 0. It's not indeterminate form. It's 10 divided by 0, and we are not allowed to divide by 0. 10 divided by 0 is undefined, and it's not fixable. The fact that we got 0 in the bottom and something other than 0 in the top tells me that the number I plugged in is a place where we have a vertical asymptote. And it's a place where I'm going to have infinite limits. So this format specifically, if you get a over 0, a can't be 0 because then that would be indeterminate and we can fix it. If you get a over 0, then you will get infinite limits. And the target x value is actually a vertical asymptote. So we still haven't answered this question, but that's a format that we can remember and recognize of, oh, okay, so this still doesn't help me with my answer, but it gets me closer to what my answer is going to be. I know I'm going to get either positive or negative infinity. It depends on what the right hand and left hand side are doing, or if they don't match up, it's going to be does not exist. So we need to see what's happening on the left and the right here. So we can look at the graph, we can make a table, or we can plug in just one number on the left and on the right and see what's happening. And I like to do that. Just plug in one really close representative number on the left and the right. So we're trying to do the limit as x approaches 2. So we need to decide if the left and the right are doing the same thing. So I need to know what's happening at 1.9. So when x is 1.9, this is going to be 5 times 1.9 over 1.9 minus 2. Five times 1.9 is 9.5. 1.9 minus 2 is negative 0.1. That is negative 95. So on the left, 1.9 is to the left of 2. It's going to negative infinity. We've already decided 2 is a vertical asymptote because we've got that format a over 0. Anytime we have a vertical asymptote, our graph is going to go to positive or negative infinity. We just have to decide which one. So because we're getting negative values on the left, it's going to negative infinity. And now pick a really close value on the right. So let's pick 2.1. So 5 times 2.1 over 2.1 minus 2. This is 10.5 over 0.1, which is 105. So on the right, it's going to positive infinity. So on the left, it's going down. On the right, it's going up. Those two pieces are not doing the same thing. And because our two pieces are not doing the same thing, we would say the limit does not exist. So analytically, we can still try our direct substitution. And the trick to identify that we're going to have these infinite limits is the a over 0. The 0 over 0 is our indeterminate form. That tells us we need to do the algebra work to fix it. But if you get a over 0, that tells us that it's going to be either positive infinity, negative infinity, or if they don't match, does not exist. So we need to kind of analyze it a little bit further on the left and the right to decide which one. So then if we want to, if we don't want to have to look at the graph or make a table, we could just see what's happening on the left and the right. We can just pick a number really close on the left and the right. Don't go too far away, because some of these graphs could cross the x-axis and flip-flop signs. We want to stay really close to our target x value. So I wouldn't go any more than 1/10. So just add and subtract 1/10. And see, all we really need to know here is whether that's going to come out positive or negative. This one came out positive. So one of them was negative, the other is positive. They're doing two different things. That means the limit doesn't exist. Now I want to look at one more example really quick with a trigonometric function. We haven't done maybe anything yet that has trig in it. Oops. We're going to try to find the limit as x approaches 0 for the cotangent of x. Now, even if you don't remember anything about cotangent, we are going to try to walk through this one slowly based on some things we know about some other trig functions. One of the most important things to remember from trigonometry class is that all of the trig functions can be written in terms of sine and cosine. So really, you need to remember everything you possibly can about sine and cosine, and everything else will fall into place. We don't really need to remember a whole lot about cotangent or tangent or secant or cosecant, because they can all eventually just be broken down and rewritten in terms of sine and cosine. And that's what we're going to do here. So I don't remember a whole lot about cotangent because I've never really had to. So what I'm going to do instead is I know that cotangent is cosine over sine. And that is a whole lot more helpful. And now if I try to do this with direct substitution, cosine of 0 is 1, sine of 0 is 0. And we got that format we just talked about that says a number over 0. A number over 0 means we have a vertical asymptote. This is that magic little form that we're going to see that means vertical asymptote. And vertical asymptote means infinite limits. Potentially infinite limits. because if they don't match up from the left and the right, we're going to say does not exist. So now that we have tried direct substitution, we have recognized that special form we got back, and we know it's a vertical asymptote and it's got infinite limits. We need to analyze a little bit further and see what's happening on this graph on the left and the right. So again, we could plug in something on the left and something on the right and see what's happening really close to 0 on the left and the right. So we could say, well, really close to 0 on the left would be a negative 10th. Really close to 0 on the right would be a positive 10th. Now you do not have a cotangent button on your calculator, but you do have sine and cosine buttons, or you may remember that cotangent is 1 over tangent. So however you want to do it, we need to figure out what the value of this function is at negative 0.1 and positive 0.1. More specifically, we need to know whether it's going to come out positive or negative. We know there's a vertical asymptote at 0. We just need to know on either side whether it's going to positive infinity or negative infinity. And I'm just going to work with my sines and cosines since that's how I have it written over here. You need to make sure that you are in radian mode because I do not have degree symbols on these numbers. These x's are in my angle position, and if there's no degree symbol, then they're automatically radians. So you would get a completely different answer if your calculator was in degree mode. Everything right now should be worked in radians. So I'm going to ask my calculator what cosine of negative 0.1 is. Divided by sine of negative 0.1. And I'm mostly interested in whether this is going to come out positive or negative. And I got negative 9.9666, about negative 10. So on the left, negative 0.1's on the left, it's going to be going down to negative infinity. And then we're going to do cosine of positive 0.1 over sine of positive 0.1. And I got the exact same number, but positive. So on the right, because positive 0.1 is on the right, it is going to positive infinity. So we've already identified 0 as a vertical asymptote, and on the left of this vertical asymptote, we're going down to a y value of negative infinity, and on the right, we're going up to a y value of positive infinity. So this x equals 0 separator line, we're doing two different things on either side of it, which means the limit really does not exist because we're doing two different things on either side. The left and the right limits are different. And you don't necessarily have to plug in these really close values the way that I'm doing this. Once you realize that the direct substitution doesn't work and you have a vertical asymptote, you can always just go look at the graph and decide it that way as well. I'm starting with direct substitution because direct substitution is a good way to start every single limit problem. And then based on the result you get from that, so sometimes direct substitution will give you your answer, and then fabulous, you're done, you circle it, you move on. Sometimes it's going to give you 0 over 0, and that tells you you need to fix it algebraically. And then now sometimes it's going to give you some other number over 0. That tells us it's a vertical asymptote and we're going to have infinite limits. A better strategy might be, once you know you're going to have infinite limits, that you want to look at the graph. Once you know it's infinite limits, you want to look at the graph and see what the graph has to say about it. That might be the best thing to do. So I'm just showing you some different options that you have. But we've already gone over the graphical, so you know what the graph looks like and what to look for here. So that's why I'm just showing you another option down here. So last thing, really quick, I'll wrap this up. I know my videos are kind of long. Really quickly, I want to talk just more specifically about vertical asymptotes. So if you see some problems that just specifically talk about vertical asymptotes, and they're not really worded like limit problems. Functions, not necessarily every single value that makes your denominator equal 0 is going to be a vertical asymptote. Because some of those values that make your denominator equal 0 might be fixable. So we've seen zeros in the denominator before when we saw our indeterminate form 0 over 0. Those were fixable. So there's two different times that we saw zeros in the bottom. 0 over 0, which was fixable, and then some other number over 0, which was vertical asymptotes. So not everything that makes 0 in the bottom is a vertical asymptote. So when we got indeterminate form, we had to do some algebra fixing. But all of those problems were presented to you as limit problems. So if you were given a problem that just asked you to find vertical asymptotes, the very first thing you would want to do is simplify that function as much as possible, because that's what we did when we got indeterminate form. That will remove all of those factors that were fixable, where we do have limits. All of those factors just create holes in the graph. And remember, with limits, holes are not a problem. We can still do limits at holes. Any factors that remain and that still create zeros in the bottom even after it's simplified, those truly are vertical asymptotes. So let me show you an example of what I mean with this. I am going to change one thing on here. I'm going to change this to a plus. Yeah, all right. So we've got f of x equals x squared plus 4x plus 3 over x squared minus 4x minus 5. We want to find all the vertical asymptotes. And we want to show our work. So we don't just want to plug this into y equals and try to do it from the graph. We want to actually show our work on how we do this. So we don't want to automatically just set our denominator equal to 0. Even though we know that from a few minutes ago, anytime we have a number over 0, it makes a vertical asymptote. It's not always the original denominator, it's the simplified denominator. So the first thing we want to do is simplify this. Because if there's anything that makes both your numerator and denominator 0, that would give us an indeterminate form, and that would mean it's fixable. We could fix it. So the first thing we need to do is try to fix this, try to simplify this. So the first thing I'm going to do is get this all factored out and see if I have any common factors in the numerator and the denominator. So my numerator, x squared plus 4x plus 3, that's going to factor to x plus 1 times x plus 3. My denominator, x squared minus 4x minus 5, that's going to factor to x minus 5 times x plus 1. And then if we have any common factors between our numerator and denominator, we can cancel them because it would be like dividing something by itself, which is always equal to 1, and multiplying by 1 doesn't do anything. So we've got a factor of x plus 1 in both of those. Now that x plus 1 is important. So the x plus 1, whenever x plus 1 equals 0, that is not a vertical asymptote. What this actually is a hole in the graph. And we're going to talk about this more in section 6, but it is not an asymptote. That factor that we were able to remove makes a hole in the graph. And you're not able to see those on your graphing calculator. So that's why we can't be 100% dependent on our graphing calculator, because it can't do everything. The pixelated screens can't show us holes. So that's something that would not show up on the graph on your calculator. So the simplified version of this function is just x plus 3 over x minus 5. And that cannot be simplified any further. So now that it's completely simplified, anything that would make the denominator 0 is going to give us a vertical asymptote. So now that it's simplified, we can set our denominator equal to 0 and solve, and we get x equals 5. That is our vertical asymptote. So this graph has one vertical asymptote at x equals 5. It also has a hole at x equals -1. And we'll talk more about the holes in section 6. But just be careful when you do vertical asymptotes. You don't always go off the original function. You have to simplify it first, because some of those factors are removable. Some of them are fixable. And that's just like our 0 over 0 indeterminate form. It's fixable. That means there are matching factors in the top and the bottom that we can fix first and try again. It's the same idea.